Hey everybody, Mr. J here. Welcome back to another episode of Chem Talks. Today we're going to continue our discussion of stoichiometry, which we started a couple days ago, with a couple little twists to it. When we're talking about stoichiometry, let's say we had a reaction. We had A plus B to give a C. We've asked questions like, if I start with 10 grams of B, how much of C can I make? Okay, but in reality, right, we have two reactants. We have A and B. So in this episode, we're going to talk about if I have 10 grams of A and 15 grams of B, how much of C can I create? Okay, and that's what limiting reactants is all about. Which one of those two reactants is going to control the production of product? Which one runs out first? And that's what limiting reactants deal with. So let's go ahead and start. We're going to start today talking about my favorite food. My favorite food in the whole world are s'mores. Yummy graham crackers, perfectly melted, lightly brown toasted marshmallow, right? Some chocolate squares on there. Those are my favorite. To make it a little bit easier, we're going to talk about the simplified s'more, which if you're going camping, this is a great camping hack for you. Instead of using graham crackers and marshmallow, or graham crackers and chocolate, you can combine those using fudge stripe cookies. Yes, fudge stripe s'mores. These are really good. Same idea, but the cracker and the cookie are kind of all in one. So if we look at these pictures, we can figure out the recipe for our s'mores, right? It's going to take 2 of the fudge stripe cookies and 1 marshmallows. Not quite as good as the original, but they are pretty good in a pinch. So if we know a little bit of information about how many we get in the packages of cookies and marshmallows, we can ask some questions. So for example, let's say in a box of these fudge stripe cookies here, in a bag of them, there are 24 cookies. And in a bag of these Jet Puff marshmallows, we get 38 marshmallows per bag. Okay. So if we have one bag of each of these, how many s'mores can we make? Well, we said we need 2 cookies and 1 marshmallow. So from a full bag of fudge stripe, we have 24 cookies, so I can make s'mores, right? A full bag of marshmallows, excuse me, I can make 12 s'mores, right? A full bag of marshmallows only needs 1, so 38. So if we have a bag of each, we can make a total of 12 complete s'mores, 2 cookies and 1 marshmallows, and we'll have some marshmallows. Now, what if we change our starting ingredients? Let's say, what if we have 2 bags of fudge stripe? So rather than 24 cookies, we have 48 cookies. Okay, so we can make 24 s'mores out of that, and we can have enough marshmallows in a full bag to make 24 cookies. Okay. What if, though, if we have 1 bag of cookies and 2 bags of marshmallows? Once again, like we said in the first example here, we can still only make 12 s'mores out of 1 bag of cookies. Doesn't matter if we have extra marshmallows, right? Same if we take it and have 3 bags of marshmallows. Adding more marshmallows isn't going to allow us to make more s'mores, because the limiting factor in this is the number of cookies we have. Right? It's a 2-to-1 ratio. Okay, let's look at this example. Go back to our original example. We have 1 bag of cookies and 24 cookies. Okay, how many s'mores can we make? Well, we said we can make 12 s'mores. When we talk about limiting reactants, some of the questions that we might ask are, how many cookies would be left over? Well, 0, because we're going to use all 24 cookies to make 12 s'mores. But how many marshmallows? Well, if we're going to make 12 s'mores, what's that leave us with? 26 marshmallows left over for just roasting or eating plain. Okay, and that's the whole idea or concept behind limiting reactants. Some products or some reactants get used up before others, and we have some leftovers of our what we call our non-limiting reactant. All right, so as I talked about earlier, most times in chemistry we have one or more reactant that we completely use up and the other is left over. Okay, this reactant that's left over, we say it's in excess, meaning we have extra of it. There's more than we need. Okay, the other one that limits how much product we get, we call this the limiting reactant. Okay, it runs out first, and when it runs out, the reaction stops. It doesn't have enough of both reactants to keep going. Okay, so we can define a limiting reactant. We say limiting reactant in a chemical reaction is the species or substance that first is used up first, runs out. Okay, it will then stop the reaction, because once there's no more of it, we can't get the other reactant reacting with it. Okay, and it's also going to determine how much of the product was produced. Even though we had 2 bags of marshmallows, let's say, we only had 1 bag of the fudge stripe. So when those 24 cookies got used up, we weren't able to make any more s'mores at the time. Okay? The other reactant, then we call the excess reactant, or sometimes you'll heard the word reagent as well. This is the reaction or the reactant that's not completely used up. Once that limiting reactant has been all used, there's still some of this other reactant left over. Okay, so our goal in this podcast is to determine which of our reactants is the limiting reactant, and then we can take it a step forward and say, okay, how much of the excess reactants remains? Okay, so let's talk about the steps there. First thing you need, just like in stoichiometry, is a balanced chemical equation. You need to have this balanced chemical equation in order to make this work. Secondly, what we're going to do is we're going to use the amount given in the problem to do a stoich problem, okay? We're going to use the amount of each reactant, so we're going to be doing 2 stoichiometry problems, and we're going to change those reactants into the same product, okay? So it's doing 2 stoich problems, which you've already done, okay? We're starting with different reactants, but we're going to go to the same product, okay? At the end, when we do these 2 stoich problems, whichever reactant gives us the smallest amount of the product that we're looking for, that's going to be our limiting reactant. The other one then is our excess reactant. Okay, so the amount of product that's actually made is the smaller of those 2 calculated values when we do the 2 stoich problems, or 3, depending on how many reactants we have. Okay, and then the formation of that product is going to stop once the limiting reactant runs out. There's no more to make it. All right, let's try this practice problem. It says, find the limiting reagent when 1.22 grams of oxygen reacts with 1.05 grams of hydrogen to produce water. So first thing we have to do is write our equation. We got O2 plus H2 to give us H2O. The other important thing is don't forget to balance it out, because these coefficients are going to be really important. So if you notice, we have 2 pieces of information given. We have 1.22 grams of oxygen as one reactant, and then 1.05 grams of hydrogen. We're going to take both of these and convert them into the same product. Well, this is pretty easy. We only have one product. It's water, so we're going to do that using stoichiometry. It's a grams to grams, so it's a 4-box problem. We'll start with oxygen first, and it is O2, so it's 32 grams. Now remember, this next step, we have to go from oxygen to hydrogen. So what's our ratio? We got 1 oxygen, the 2 hydrogen, or 2 waters, right? We want water, so 2 moles of hydrogen is going to go on top. 1 mole of oxygen goes on the bottom, and then we'll convert that into grams. So 1 mole of water, if you remember, weighs 18.02 grams. And we get a total production of 1.37 grams of water. We'll do the same thing, but we'll start with hydrogen. Okay, so a little different starting there. And we have a 2-to-2 ratio, so 2 moles of hydrogen per 2 moles of water, and then we'll convert it into grams again, and we get 9.37. So if we look, we can see we produce much less water starting with oxygen than we do hydrogen. Okay, so if I was asking how much we'd produce 1.37 grams of water, and oxygen's going to be our limiting reactant. It stops. Once this 1.22 grams is used up, we're not going to make any more water, so we just kind of ignore this. Now, because this problem asked for the limiting reactant, we could have actually stopped right here at moles. Okay, it's not asking how much is produced, it wants to know that. We get our answer in moles, and if we did this, we'd find oxygen gave us 0.8 moles and water gave us 0.52 moles. So once again, we'd see that this water produced from oxygen is a smaller value. Okay, so we know that oxygen is our limiting reactant. So when you're doing problems like this, if they ask what's the limiting reactant, stop at moles. You don't need to do that. But they're asking if how much is being produced, then you do want to go to gram, because when we're asking how much, we're asking grams, not moles. All right, let's try another practice problem here. So a 2-gram sample of ammonia is mixed with 4 grams of oxygen to produce nitrogen monoxide and water. We can ask how much nitrogen monoxide can be produced. And then our kind of part 2 of this, how much of the excess reaction remains after the reaction has stopped. Okay, so this is the extension to it. So first thing we're going to do is, well, we have to write a balanced equation. We know that ammonia, NH3, remember, not NH4+, plus oxygen to produce nitrogen monoxide. So NO. So there's our equation. And is it balanced? Let's see. I got one nitrogen, three hydrogens, and two. Oh, so you go ahead and I have to balance this. So when we balance it, it looks something like this. This is really important to remember because we need those coefficients to switch from one product to the other. So now let's do the stoichiometry. Okay. So we want to find which one's the limit and how much we're going to produce. Okay. So it gives us the information here. We're going to start with 2 grams of ammonia. Okay. And then we go to moles of it. Now we're going to use our balanced chemical equation to figure out how much nitrogen monoxide, right? So every 4 moles of nitrogen monoxide, we need 4 moles of NH3. Even though it's a 1-to-1 ratio, you still need to do this because we're showing how we're going from ammonia to nitrogen oxide. And then finally, we're going to convert it to grams, okay, using the molar mass. Same thing, but we're going to start with 4 grams of oxygen, okay? And it is 32 because we're talking O2 right here, right? And then what's our ratio here? We need, for every 4 moles of NO, we have 5 moles of NO2, okay? And then once again, we're going to figure out our molar mass, which is the same as above, makes it easier. So we can see when we combine these two things, our smaller value is 3.0. So we're going to produce 3 grams of nitrogen oxide. All right, so that's part A. How much nitrogen oxide are you going to produce? 3 grams. Okay. Part B then asks us how much excess remains. Okay, how much of that, what was it, NH3 is going to remain after we use up all the O2. Okay, so what we're going to do in this case is we're going to change to calculate the excess reactant. We need to know if we use up all of our limiting reactant, which in this case was oxygen, how much NH3 are we going to use? So we're going to start with our given amount of oxygen and change it into NH3, which will tell us exactly how much NH3 we're going to need. And then we can take that amount, subtract it from the amount of NH3 we started with, and that will give us the reactant. Okay. Now, there are a couple ways to do this. I'm going to walk you through this one, and I'll tell you why. So we convert our 4 grams, right? Here's our molar ratio from the equation. We find out that we need 1.7 grams NH3. Now, I like doing it this way because I know this value of 4 grams of oxygen. Now, I could have used the amount of O2 we made, or excuse me, amount of NO that we made, and change that to NH3. But the problem is I had to do several calculations to figure out that amount of NO. If I messed something up in there, I'm going to be starting with a value that wasn't given to me. So I always like to convert from my known reactant value to figure out how much of the other reactant I need. That way I know these problems. Well, from the problem, it says I think I started with 2 grams of NH3. I need 1.73 grams. So the amount of NH3 left over is just the difference between these, which is 0.27 grams NH3 left over. Okay, so we had to do a total of 3 stoic problems here and a subtraction problem to do this. Let's look at another problem. Okay, actually, let me have you do this one on your own. It says, what is the limiting reactant when 50 grams of silver metal reacts with 10 grams of sulfur to form silver sulfide? How many grams of the non-limiting reactant remains? That's the excess, okay? So go ahead, pause the video here, please. Do pause, okay? Work this problem out yourself and then come back. All right, hopefully you've paused this and not just cheated waiting for me to give you the answers, because that's not going to do you any good in the test. All right, so the first thing we have to do, right, is to make a balanced equation. So silver plus sulfur gives us silver sulfide, right? Remember, +1 for Ag, -2, okay? So make sure we're doing that. And let's see, they give us grams, and they want to go to grams, so it's going to be 2 4-box stoic problems, okay? So the first time, we're going to start with 50 grams of silver, okay? And there's our molar mass, there's our ratio, 1 silver sulfide to 2 silver, and we end up with 57.43 grams of silver sulfide. We're going to do the same thing, but starting with sulfur this time. Okay? It's a 1-to-1 ratio. And look at this, even though we started with less sulfur, it's going to give us more. So the amount of silver sulfide that we actually produce is going to be the less of the two, and that's 57.43 grams. Okay, that's the answer to part 1, how much we're going to produce. Because once this 50 grams of silver is used up, the reaction stops. Now what we're going to do is we're going to change our limiting reactant Ag into sulfur and figure out how much sulfur do we actually need to react with 50 grams of silver. Okay. So once again, we set this up just like we did before, and we find out that, hey, we need 7.43 grams of sulfur. So we didn't need that 10 grams. So to find out how much is left over, we're going to take our 10 grams and subtract the amount that we would need to exactly react with 50 grams. Okay. And we find that we have 2.57 grams of sulfur remaining in excess after this reaction has occurred. Okay, so once again, 3 stoichiometry problems and a subtraction problem. Not too bad. All right, let me show you the alternative way of this. We figured out that when we started with our 2 different amounts of reactants, we were going to produce 57.43 grams of silver sulfide. I could also ask the question, well, how many grams of sulfur would I need to make that amount? And the same thing as we did with changing silver into it. Okay, we need 7.43 grams, and we can then take 10 minus 7.43, and we get the same thing. But remember, in order to get this, we had to go through this a couple times. And if we messed up our molar mass here, or we messed up our molar mass there, this could have given us the wrong 57.43. That's why I like to, instead of using the original product, I like taking the original reactant, the limiting reactant, and converting it into the excess reactant, because both those values were given to us in the problem. All right, guys. So that is limiting reactants. It's looking at which one of our reactants will run out first, and then how much of the other reactant, our excess reactant, remains. We will do a lot of practice in class. If you have any questions, please come see me before class or ask questions in class. Until next time, guys, take care. I'll talk to you soon.